I'm Dar-bin Shieh. I'm from National Cheng Kung University. It's in South Taiwan, tropical area, very nice weather. All right. This is about, this is small in Taiwanese characters, at least, oh yeah. And how small is a nano? I'm actually working with nanotech for the past decades. For example, if I'm 2 meter high, if I look at an ant, it's about 1,000 times down size. It's about 10 to the minus third, right? And then if I'm an ant, if I look at E. coli, bacteria, it's another 1,000 times downscale. And then if I'm an E. coli, and I look at nanoparticle, it's another 1,000 times. So that gives an idea of how small nano size is. Well, in that kind of nano, in Taiwanese letter, it's an integration between the big and small, right? Which means that is the size between the bark and the real small mean atomic or subatomic particles. And that gives you a big inspiration. Okay. So then I told you, I'm going to tell you how this kind of doing things small can change the world. Well, here this is a DNA. It's about 2 nanometers in width. And basically, technically, it's a nanomaterial. And this is the virus that gives you a common cold or sick. And it's a particle of about 30, 40 nanometers in size. All right. In the past, life has been evolved since billions years ago from the molecular levels. And you can see that this is a lot of different proteins that can form different kinds of structure to exert different functions in your body. So you can sit here and listen to my talk. Now, scientists can fabricate a lot of materials and also kind of control their size at nanoscale. These are all the materials we did in my lab. Like this is a beautiful rose, which has only a size of 200 nanometers. Of course, you probably want to send to your girlfriend, but you may need to send her expensive electron microscopy too. And we can utilize biological materials as a building block of nanoparticle too. For example, here, this is a nanoparticle of defined size made of DNA, the genetic building block of your inheritance. And this is the empty particles. All right, so I'm going to show you since this kind of size can actually cross-talk to the biological system because they have a comparable size domain. And how can you utilize such kind of concept, cross-talk to your pathogenic bacteria, cross-talk to the virus, or cross-talk to the cancer cells? And now, of course, you have to fabricate something that's really small and really smart so that they can talk to the pathogens or life systems at nanoscale. How can you do it first? It's actually pretty simple. You have a water solution, and you contain some of the, for example, this is sodium chloride, and then you just change their temperature and the solubility. And with ultrasonic, then vibration, you will fabricate very, very tiny crystals, right, by precipitation. And because of their surface charge, now you give them polymers, so the polymers will automatically attach on the surface. Then the particle becomes another charge, for example, from positive to negative. So that you give them another kind of positive charge polymers. So they will kind of coat it on the surface again. And do this again and again and again. Now you form a layer by layer stitching of polymers on top of the crystals. And finally, you want to put something that is smart enough, like to make a little virus-like particles. Right. This is a really small, about less than 100 meters in size. Now, if you can coat these particles, for example, you just brush your teeth and rinse this particle, the particle will just automatically attach onto the surface because of the surface little fingers. They are designed to attach on the tooth surface. So if you have a lot of bacteria in your mouth and they attach on the surface, the particles start to cross-talk with the bacteria on top. And because the pathogenic bacteria, they produce very acidic environment, which is a key to open up the polymer pores, and then the ingredient of the sodium chloride will be released. And because they are so small, smaller than the bacteria, so only this smaller area will release the sodium chloride. And then, of course, you will see this. This bacteria get killed, and this bacteria don't, because they don't secrete so many acids. And finally, you will find all your oral cavity are filled with good bacteria, probiotics. Well, this is a particle. See, this is a 100 nanometer of size. If you look carefully, you see the cross-stitched, and this is the kind of polymer surface. And then you assemble the attachment filling on top of it, so make it like this. And you can make a lot, tons of this. And because under very acidic pH, the ingredient was kind of released abruptly, while in the low pH, they are kind of constantly gradually released. So this is the bare piece, and this is the assembly of the particle on the piece surface. Now, if you have a pathogenic bacteria, it will get killed because they secrete a lot of acid. If you have probiotics, they live safely on top of it. So such kind of rebalance your oral flora rather than kill everybody. And from molecular level, close up. All right. So, nanoparticles are even smaller than the bacteria. So how about can the nanoparticle crosstalk with your biological molecules? And what we did, can you control the gene deletion or even editing by light, by electromagnetic wave? Nanoparticles, they have a very unique physical property and optical property, so that they actually interact with electromagnetic waves. So that if you have a gold ring, if you make them into gold nanoparticle, very, very small gold nanoparticle, they just look like beautiful red wine, red color, because they absorb green light. All right, we know that genetic codes constitutes the secrets of life. And if you can kind of cut and paste genetic codes, you are able to design life. And DNA makes RNA, RNA makes protein, right? And protein exerts all the biological functions. So if you can edit, you can cut it, and you can edit, you can basically change life. And in the past decades, people have discovered so-called nutrition enzyme to do the kind of genetic editing. And however, the nutrition enzyme normally only recognize very few bases. So if you use a genetic, you use the nutrition enzyme to cut your gene, you will basically chop off everywhere in your genome and disrupt everything. So we need a more precision tool for that kind of genetic editing. And DNA double helix has been discovered in the last century. However, let people remember that in 1957, scientists already know DNA can also form triple helix, and by design. So we utilize such kind of concept, and we form a DNA editing nanoparticle. This particle has a third strand DNA design to recognize specific gene sequence. And in our design, we can even recognize 30 base pairs, which give you 4 to the 30s of the specificity. And because such kind of sequence after recognition, if you want to cut it, we want to use the electromagnetic wave to control the cutting. So we designed a warhead here, which generates a radical pair to cut the phosphodiester bond of the double helix. And of course, you don't want it to randomly cut, so we use the nanoparticle as a quencher. Since nanoparticles, they absorb specific wavelengths, so that if we design this DNA as a loop structure, when there's a electromagnetic wave coming in, if it's not recognizing the DNA sequence, it will be quenched by the particle surface plasma. If it's a specific, then it's away from the surface plasma, then it can exert its cutting. And so this is the video describing how we do it. So first we assemble a lot of this kind of DNA recognition, DNA. And then we assemble this molecular cutter, which will generate two radicals here. We cut the phosphodiester bond. And to be safe, we use the surface plasma to control all these cutting warheads. And if you have a green fluorescent expression cell, it is well known that DNA gold nanoparticle complex is very efficient in delivering gene materials into the cell. And when it gets to the lysosomal compartment, they can escape and then go to the nucleus. And we use shiny or blue light and generate radicals and cut the DNA. Then you silence the gene, or you open an opportunity to edit the gene. All right, so this is a green fluorescent cell. And this is after elegans treatment, and then shining the light, and all the fluorescents are gone. Then we play a trick. This is a gene called STAT3 that related to cancer drug resistance. And there are two isoforms. One will be expressed from number 1 exon to number 23rd, and the other will be expressed to the 24th. And we want to erase only the second isoform. So we designed a targeting sequence here. And you can see that it forms triple helix, so that its migrate slower because it becomes heavier in molecular weight. And in the protein level, we only erase the isoform alpha and leave the beta to exert no function. And now we are moving forward and successful in erase gene from whole animal in C. elegans. So this gives you an idea that actually nanoparticles can do a lot of amazing things, even gene editing. For example, you can design even more complex particles like this with a targeting antibody, with a polymer to carry drugs, with a core of iron oxide particles, so that when you're shining electromagnetic wave, it gives a response of electromagnetic wave. And then such kind of electromagnetic wave can be picked up by an MRI sensor, so that you make beautiful MRI contrast imaging. And it's so small so that you can target to a specific cell type, for example, cancer cells or infectious pathogen. And moreover, if you give the right electromagnetic wave that can resonance the particle, and then they will generate heat, and such heat will release the drug from the particle surface and directly attack the cancer cells, so that the cancer cells will be damaged by both physical energy of the heat and at the same time by the chemical ingredients of the chemotherapeutic agent. And this gives you a perfect remission of the tumor growth. And you can even design multi-layer symbiotic particles and give a selectivity, only kill the cancer cells, not the normal cells by their metabolic state. They only deplete the mitochondria charge in cancer cells, but not the normal cells. And so that you can see that not like the conventional chemotherapy, which patients normally lost their weight. They give a very healthy, patient, and then they kill the cancer cells post-dependently. Well, although you can see obviously that engineering at a small scale can give a lot of opportunities. However, if you think about people can edit specific gene and can kind of erase specific gene, it is also an opportunity to do bad things. So we're in the middle, we're facing the past and facing the future. And I think the story is just to be continued.